All right, here's the situation. You've got glass, where the index of refraction is given as 1.51. And then on top of that, you have a thin film of alcohol. And the index of refraction is given as 1.36 for that. We're going to shine monochromatic light, which means light of one wavelength, or a laser, down on it normally, so approximately perpendicularly. And this laser, we're able to adjust the wavelength to whatever we want it. So they say that when we use 512 nanometers, which is kind of green, it returns a minimum. So this little picture we have in the notes here, those two beams, since it returns a minimum means minimum amplitude, so we're going to have destructive interference. So that was the 512 nanometer light. However, when they shine 640 nanometer light, which is reddish orange, I'll just use red. It will undergo this process. You get these two beams like in the notes, and this time it returns back a maximum. So they're saying it returns back pretty bright, meaning we have constructive interference. So that was for 640 nanometer light. So our goal is to find the thickness here, basically find T, the minimum value of T, such that we get constructive interference. When the wavelength is 640 nanometers. And at the same time, for the same thickness, we have to get destructive interference for the other wavelength. So I'm going to make two headings here. My first heading, I'll analyze the green light, the 512 nanometer light. First of all, let's analyze phase shifts. Beam 1, which is air, to alcohol, that's going to involve a phase shift. Because we're going from a faster to slower medium, air to alcohol. Beam 2, that would be alcohol to glass. So let's see, alcohol has an index of 1.36, and glass has an index of 1.51. So actually, again, we are going from a faster to slower medium, so we will have a phase shift as well. The beams are in phase. And with all of that thought about and analyzed, we can now pick out the equations we need. So for the green light, we want the beams have got to be in phase, and it's got to be destructive interference. So 2t, in that case, to make a destructive interference, they would have to be off by a half wavelength in the film. I'll use N to stand for, well, that'll be alcohol's index of refraction, because alcohol is the thin film here. Meanwhile, for the red laser light, so 640 nanometers, we want constructive interference, so we want 2t to be an integer multiple of lambda in the alcohol. I'm going to put some numbers into both equations and isolate for the thickness as well. So the lambda is 512 for the green, and isolating for thickness, I divide both sides by 2, and the index of the alcohol is 1.36. And over on the red side, same thing, divide both sides by 2. The wavelength, sub it in as 640. The index of the alcohol, sub in 1.36. Okay, I'm going to simplify the numerical parts of these. So 512 divided by 2, and also divided by 1.36. Gives me 188.2. And on the red side, 640 divided by 2, and also divided by 1.36. That is 235.3. So with these two equations, I can come up with possible thicknesses for each side, and until I can find a common thickness. That will be my strategy. So, green. I'm going to make a table of values here. I'm going to have various values of m and use the formula above to figure out what thickness it would be. Do the same thing with the red. Use various values of m and figure out what the thickness will be until I can find a common thickness amongst both tables. All right, so let's start with the green. If m is 1, I'll have half times 188.2. So that would be 94.1. If m equals 2, it'll be 1.5 times 188.2. That'll be 282.3. And as I increase the m value by 1, I'm basically going to increase my thickness by 188.2. So when I plug in m equals 3, the result's going to be 470.5. When I plug in m equals 4, the result will be 650. 58.7. I may have to do some more, but I'm going to try a few on the red side. Okay, I'll plug in m equals 1. That's simply 235.3. So does that match anything on my green table? No, it doesn't. So I'll plug in m equals to 2, which is just a double of 235.3. That's 470.6. Okay, so actually, that's extremely close to one of the values on the other table. So when I have a thickness of, to 3 significant digits, it'll be 471 nanometers. Then I will satisfy both conditions, the conditions being that the green laser will be reflected a minimum and the red laser will be reflected a maximum. So our answer is going to be 471 nanometers.